Hi everyone, my name is Christian Wing and I'm doing video presentation problem number 2 for week 4, section 3.2, number 14. And so in the book, it's in the 3.2 problems, the directions are find general solutions in powers of x of the differential equations in problems 1 through 15. State the recurrence relation and the guaranteed radius of convergence in each case. And so the problem is this one, number 14, right here. Um, y double prime plus x times y equals 0, and it says it is an Airy equation. Let's figure out what that means. Yeah, I rewrote it. Here's my work. And so I did a little research, and the area equation is something in the form of y double prime plus or minus a constant squared times xy equals 0. Luckily, this one was a pretty standard example. And so I started out doing kind of the same thing as usual. To sub in a power series, you need to get to the second derivative. So of course, first one is y equals summation n equals 0 to infinity, uh, constant times x to the n, and then take two derivatives of that. Sub them back in to your original differential equation. Um, and so we have x to the n minus 2 and x to the n. And that is not good. We need to use um, a dummy variable to get these guys the same. So we let k equals n minus 2, so n equals k plus 2. So we sub that in as well and change those. So we have x to the k, but this x over here combines with this x to the n and gives us x to the n plus 1. So now we have another discrepancy once we sub an n back in for this at a later time. So we need to use another dummy variable and let p equal n plus 1, and so n equals p minus 1. So that's good. Now we have another single single letter up there that x is raised to. So that's good. Only problem is that we start at different numbers here. This one starts at 0, this one starts at 1. We cannot do that. We cannot use uh, our power series operations. And so what we can do is for this guy over here, we can split off the 0th, I guess, term of the first sum over here. And so that would, if we split that off, we can get this to n equals 1 and start at the same time this does. And so here's that rewritten. And then here's the 0th term. Of course, this is n plus 1, which would be the 0 plus 1, 0 plus 2. C to the, or C sub n plus 2 is, C 0 plus 2 is C sub 2. And then x to the 0 is 1, so this is your 0th term, plus the remainder of your sum. And so this has a nice n equals 1, and it starts at the same time as that. So that's good. So now we can combine these with our power series operations, which is good. Factor out the x to the n, and our identity principle gives us two things. It gives us 2 times c2 equals 0, and it gives us our um, n plus 1 times n plus 2 times c n plus 2 plus c n minus 1. And so we need to solve for the highest degree of c. So that gives us two important things here. Our recurrence relations, c2 equals 0, and cn plus 2 equals negative cn minus 1 over n plus 2 times n plus 1. So those are recurrence relations. We'll use those later, and we'll use those as we kind of explore the recurrence relation. And so you write out multiple values of n and kind of investigate uh, what kind of pattern goes on here. And we notice that every third term is, or I guess every first term in a series of 3, however you want to describe it. Anyway, every third term is 0. And so And we can also see that so the second and third terms are negative, and these fifth and sixth ones are not negative. And then if you were to go on, you would get the sixth, eighth, and ninth terms would be negative as well. So it would alternate there too. And so basically the patterns we get are so every, we'll say, I don't know, every third term. Yeah, sure. Uh, every third term, so starting with, C sub 2, which would be the third term if you include C sub 0, um, every third term equals 0 for all n integers. Um, and then we'll say, first term, this is the pattern we get for that. The important part here is the n, 3n minus 1 times 3n. You can kind of see the pattern going on here in this one. Um, and so we notice that every first term is with respect to C sub 0, and every second term is with respect to C sub 1. And that is this pattern there for that constant. And so continuing on, when we write out a power series for y, so C sub 0 plus C sub 1x, and then C sub 2 x squared, every third term again will be 0. And so then we can see kind of our pattern here where these, uh, you know, what, fourth and fifth terms will be negative, and then the sixth and seventh ones will not. And so to do that, obviously, uh, the um, every third will be 0. So we're left with our first and second, I guess, of the pattern of 3. So here's the first one. Again, 1 plus the rest of our sum. This is important. Every third term, or I guess we'll say first term should be negative, and then you keep going and you get positive for these guys. Um, and then obviously the second term in your trio of, I guess, the pattern of 3, um, do the same. And so yeah, that is not a recognizable function, but it is quite a different case. So now the radius of convergence, I must have a disclaimer here and say this is just kind of a guess I did, since your regular radius of convergence, you find rho equal to the limit as n approaches infinity uh, of Cn over Cn plus 1. Nowhere in our recurrence relations did we see either of those, I guess, explicit constants, really. We were just exposed to Cn minus 1 as well as Cn plus 2. Um, and so my theory was let let 3n equal x. And so then here, what we are given, we get kind of this relationship here, which is very similar to that. So um, if we sub in from our constants here, what we got for those, with obviously subbed x for 3n, do a little simplification here, and eventually we get uh, x plus 1, or negative quantity x plus 1 over x minus 1, which plus 1 minus 1, very close to x over x, which is very close to, or which is 1, negative 1. And so your radius of convergence would end up being negative 1. So this also confirms my research, where it does, um, I believe, the, what's it called, the Airy equation said something about it between P of x and Q of x, it does converge to at least one of those, and so, or yeah, at least one of those. And so, yes, it does converge to -1. So thank you.